In the last video, we built sample spaces and events, the stage every experiment plays out on. Now we put numbers on those events. A probability law is the rule that assigns each event its likelihood, and remarkably, it rests on just 3 axioms. In this video, we meet the 3 axioms themselves, the consequences they force, like the complement rule and monotonicity, the formula for the union of 2 events, and the union bound a workhorse inequality. By the end, every rule you will ever use for combining probabilities will trace back to these 3 axioms. Start with the central object. A probability law assigns to every event A a single number, written PR of A, that measures how likely A is. Picture the sample space omega as a region and an event A as a patch inside it. The probability of A is the amount of mass sitting on that patch. 2 events that look very different can carry exactly the same probability. All the law records is how much weight we attached to each. In other branches of mathematics, the very same object is called a probability measure, a name that emphasizes its status as a set function. It is a name we will follow up when we reach measure theory. The first axiom is non-negativity. Every event gets a probability that is at least 0. Weights are never negative. The second is normalization. The whole sample space carries probability exactly 1. Something in omega is certain to happen, and certainty is 1. The third is additivity. If 2 events A and B are disjoint, they share no outcomes, then the probability of their union is just the sum of their probabilities. Non-overlapping masses simply add. That third axiom is the engine of the whole theory, so let us spend some time with it. Here are 2 disjoint events, A on the left and B on the right, with no overlap between them. Because they are disjoint, the probability of A or B is exactly the probability of A plus the probability of B. Nothing is double counted because there is no shared region to count twice. But the axiom says more. Additivity holds not just for 2 disjoint events, but for a whole infinite sequence of them. Take disjoint events A1, A2, A3, and so on, tiling the sample space with no overlaps, a partition, exactly the structure we met back in the sets video. This is where probability outgrows mere counting. The pieces need not be finite in number, only pairwise disjoint. The probability of their union, the chance that some one of them occurs, equals the infinite sum of the individual probabilities. Picture the pieces as a half, then a quarter, then an eighth, and on forever. The masses add up to the whole. Finite additivity is just the special case where all but finitely many pieces are empty. The countable version is strictly stronger. This is countable additivity, and it is exactly what we need to put probabilities on infinite sample spaces, like tossing a coin until the very first heads where there are infinitely many possible outcomes. The axioms immediately force a string of useful rules. Take any event A and its complement AC, everything in omega outside A, they are disjoint, and together they fill the whole sample space, so by normalization and additivity, their probabilities add to 1. Rearranging, the probability of the complement is 1 minus the probability of A. It is often far easier to compute the probability of what you do not want and subtract, a trick we will reach for again. As a special case, let A be all of omega. Its complement is the empty set, so the impossible event carries probability 0. Next, monotonicity. Suppose A sits inside B. Then we split B into A together with the part of B outside A, 2 disjoint pieces. Additivity says PR of B equals PR of A plus the probability of that left over, and since probabilities are never negative, PR of A is at most PR of B. A bigger event is at least as likely. This has a consequence human intuition routinely violates. Because A and B sits inside A, the probability of a conjunction can never exceed the probability of event A alone. Adding detail to a description can only lower its probability, never raise it. Yet people reliably get this backwards. In a classic experiment, respondents were told that someone is politically active and outspoken, then asked which is more likely, that the person is a bank teller who is also active in a social movement, or simply a bank teller. Most people chose the former, even though it is a special case of the latter, and so can only be less probable. The richer, more representative story simply feels more likely. Ranking the more specific scenario above one of its own constituents is the conjunction fallacy. What if the two events do overlap? Here are A and B with a shared lens in the middle. If we simply add PR of A and PR of B, we count that overlapping lens twice, once for each circle, so we subtract it back out once. In general, the probability of A union B equals PR of A plus PR of B minus the probability of their intersection. Add the parts, then correct for the double counting, and notice that when A and B are disjoint, the intersection is empty, and we recover plane additivity. The same bookkeeping extends to any number of events, alternately adding and subtracting the overlaps of overlaps of overlaps. That general pattern is the inclusion-exclusion principle. For 3 events, you add the 3 single probabilities, subtract the 3 pairwise overlaps, then add back the 1 triple overlap. The signs alternate all the way up. We state it and move on. Sometimes the intersections are hopelessly hard to compute. Then we settle for a bound. Drop the subtracted overlap terms from the union formula and the right side can only grow, so the probability of a union of events is at most the sum of their probabilities. Applied repeatedly, a quick induction, this gives the union bound, also called Boole's inequality, for any number of events. Here it earns its keep. An urn holds 990 blue balls and 10 red ones. 5 people each draw a ball without replacement, and we want the probability that at least one of them draws red. The union of the 5 events, person K draws red. Each person on their own has a 1 in 100 chance of red. The union bound just adds those up. 5 times 100th is 1/20th, or 0.05. That is an upper bound, and it took almost no work. The exact answer needs the probability that nobody draws red, a ratio of binomial coefficients, which comes to about 0.049. Remarkably close to the bound and far harder to reach. That is exactly when the union bound shines, when the individual probabilities are simple, but the joint event is not. As a second application, suppose each of the 5 people draws 2 balls instead of 1, and we ask for the probability that someone ends up with 2 reds. The same union bound applies with almost no extra work. 5 times the chance that a single person draws 2 reds, which totals 1 in 2,220. But computing the exact value here is genuinely hard, and that is exactly the situation the union bound was made for. So the whole of this video rests on 3 axioms: non-negativity, normalization, and additivity, and everything else, the complement rule, monotonicity, the union formula, and the union bound, follows from them. Next, we meet 3 families of probability models: finite countably infinite and uncountably infinite sample spaces.